This study unit covers the basic PDP-11 console. The operator uses the console to start the computer and then to manually intervene in the operation whenever required. We're all familiar with the automobile dashboard. The dials, switches, and indicator lights are necessary for the safe, efficient operation of the car. Driving a car without these controls would be virtually impossible. They're as important as the gasoline in the fuel tank. Similarly, the console, as the man-machine interface, allows the operator to run the computer. Like the car, the computer cannot operate by itself. It must be guided, either by stored instructions or by the computer operator. The switches and indicators on the console provide the means for the operator to do this. Several variations of the PDP-11 console are provided to meet the different customer requirements. It might be noted at this point that we're going to use the PDP-1140 console as the example in most of the visuals. For our purposes, we can consider the 1140 console as typical of all the PDP-11 consoles. Now, let's take a look at the major topics to be covered in this study unit. First, we're going to look into the use and operation of the basic console controls. After we learn how the basic controls function, we'll explain how the console can be used to load, examine, and start small programs such as the bootstrap loader. In providing the communication link between the operator and the system, the PDP-11 console performs 5 basic tasks. The console controls are divided into 5 groups of switches and indicators, one group for each of the assigned tasks. We'll now look at each task in turn and the group of console controls that are used to perform the task. The first task is to apply power if the system is not already on, just as the first step in starting a car is turning on the ignition. System power is controlled by a single switch. In most PDP-11 consoles, this is a 3-position key-operated switch. The console also allows the operator to load small programs and data into memory. The PDP-11 uses the program to tell it what to do. The program, in turn, operates on the data to accomplish this. A group of switches is provided for manually loading information, that is, programs and data. This is not the only way we can get information into the computer, but it's the only way it can be done manually at the console. We'll discuss this in more detail later. Information display is another function of the PDP-11 console. Both data and addresses can be displayed in octal format. Data could consist of instructions or data words or the contents of a register within the processor. Indicator lights are provided for both addresses and data. As we will see shortly, some consoles use the same set of lights to display both types of information. The 4th basic task performed at the console is controlling system operation. This is commonly referred to as manual intervention. Our program has to be started, and then, unless it's written so as to halt itself, must be stopped at some later point. Remember now, a program start is different from the power start we talked about previously. Console operations are controlled by several switches located to the right of the data switches. The number of switches available depends on which console is used. Finally, the console allows the operator to monitor the system when maintenance is being performed on the hardware. The programmer may also want to monitor system functions when debugging his software. Indicator lights are provided on the console for monitoring system operation. The number of indicator lights will vary depending on which console is being used. Let's quickly review what we've just covered. The basic PDP-11 console performs 5 primary functions or tasks. They are apply system power, load programs and data, display information, control operation, and monitor operation. 5 groups of controls are used to perform these tasks. As you can see, the controls are closely related to the tasks. The console switches and indicators are positioned according to function. There are 2 general switch and indicator configurations, one for the 1105 and 1110, and one for the other consoles. Now that we've defined the jobs done by the console, let's take a closer look at the switches and indicators used to perform these jobs. We'll begin again with power control. Power is controlled by a single key-operated switch. The switch has three positions: off, power, and lock. It controls the power to the entire system, including peripheral devices. To operate the switch, the operator inserts the key and turns it to the desired position. In the power position, primary power is applied to the system. All console controls are operable at this time. In the lock position, power is applied, but console control switches such as load address and start are disabled. This prevents inadvertent interference with a running program. Next, we have the load controls, commonly referred to as the switch register, or SR. The switch register is used in conjunction with several control switches. We'll see how this is done in a little while. The switch register is used for loading both data and addresses into the system. The 1105 and 1110 have 16 switches. Other consoles, such as the 1145 and 1170, have additional switches to accommodate the expanded 18-bit or 22-bit address. Let's look at these switches a little more closely. Depending on the particular console, the switches are either of the toggle type or the rocker type. In the up position, the switch output represents a logical 1. In the down position, the output is a logical 0. Thus, each switch represents one bit of information. The switch furthest to the right corresponds to the least significant bit, or LSB. The switch furthest to the left corresponds to the most significant bit, or MSB. Since the operator usually enters an address or data in the octal format, the switches are color-coded in 3-bit segments. This helps to prevent mistakes when placing a number in the switches. The switch register can be accessed by the computer program at any time, regardless of the console mode of operation. Its address is 777-570. What's the purpose of giving the SR an address? Well, it allows the operator to control program operation and to enter data when the program requires, while the program is running. Since the SR is addressable, its switch contents can be read during the execution of a program. The operator simply sets the SR switches to some predetermined configuration. An instruction in the program then reads this information and uses it to guide the course of the program or to supply some needed data. Thus, the operator can enter information into the system while the program is underway. Both the program and the operator control system operation, not just the program alone. Let's take a look now at the next console group, the data and address indicators. The data and address indicator lights present the operator with a visual indication of the current address and the data contained at that address. The displayed information is used primarily when going through a program step by step to look for hardware or software errors. On the 1140, the address portion of our display contains 18 lights. Addresses normally consist of 16 bits, but 2 additional lights are provided for the expanded 18-bit address that is generated by the memory management option. The address lights relate directly to the SR switches underneath them. A color-coded bar above the lights makes it easier to translate the light configuration into an octal number. Note that the color coding matches that used for the SR switches. The 16 data lamps are located immediately below the address indicators. Only 16 data lights are provided, since no PDP-11 data word can exceed 16 bits. Again, there's a direct bit relationship with the SR switches. The color-coded bar above the lamps serves the same purpose it did for the address lamps, to aid the operator in reading the octal equivalent correctly. The 16-bit data word, as we previously learned, consists of 2 8-bit bytes. An index mark on the color-coded bar above the data lights helps the operator to separate the word into its 2 bytes, the high byte and the low byte. Each of the 2 bytes have 8 bits. This means that the most significant digit of each byte is derived from its 2 high-order bits. Consequently, the most significant digit of a byte can never be greater than 3. Notice that when the high byte is read alone, its octal digits change from when the entire word was read. This is because the bits are shifted 1 position to the right. The index marks help the operator to read the octal digits that make up the high byte. We've been talking about the display indicator group as it's found in the 1140 and similar consoles. The 1105 and the 1110, however, have a different light configuration. In the 1105 and the 1110, the display indicators consist of one common set of 16 lights instead of the two sets that the other consoles have. These lights display either the current address or the data at that address. The switch register and the display indicators do not function by themselves. They respond to some action or series of actions that the operator takes with the control switches. We'll now take a look at these switches. The control switches located on the right side of all consoles are used for several purposes: to load information into the system, to examine the information in different locations, and to perform certain system functions such as start, stop, and continue. These control switches work in close relationship with three other console groups we've discussed: the switch register, the address indicators, and the data indicators. One of our control switches is a momentary switch called load address. It is used to provide an address for the deposit, examine, and start functions. Pressing load address transfers an address that had been previously placed in the switch register to a temporary location within the processor. From here, the address is sent to the bus address register, or BAR, where it can now be used to address devices on the Unibus. Load address, when pressed, also causes the address in the switch register to be displayed in the address indicators. Remember now, loading the address is a prerequisite for the deposit, examine, and start switch functions. This is a good example of multiple console actions that are required to accomplish a console operation. Let's look at two of these switches, deposit and examine, at this time. We'll come back to the start switch later. The deposit switch might be considered as the write or store switch, since it's used to store data in memory. But it can also be used to load data into a GPR or a peripheral register, and therefore we use the term deposit instead of store. The deposit switch transfers the contents of the switch register to the location displayed in the address indicators. There's an exception to this, as we'll see in a few moments. The switch is activated by lifting rather than pressing down. This prevents inadvertent loading of data. Since this is a momentary switch, it returns to the normal position when finger pressure is removed. At this time, the SR data is shown in the data indicators and the affected address in the address indicators. Do you think we could deposit several words in successive locations? Let's try. We'll begin by assuming that we want to deposit the first word in memory location 100. We place 100 in the switch register and press load address. This establishes our starting address. After the first word is placed in the SR, we use the deposit switch to load this word into memory location 100. Now the second data word is placed in the SR and the deposit switch is raised again. This action increments the address by 2 so that the second word is stored in memory location 102. Thus, we can deposit data in successive locations simply by repeatedly raising the deposit switch. The load address operation has to be performed only once at the beginning. Depressing either load address or examine interrupts the address incrementing sequence maintained by consecutively lifting the deposit switch. Load address, for example, allows us to deposit data in different memory areas. Remember now, the new address has to be placed in the SR before load address is pressed. Then the next data word is placed in the SR and deposit is raised. Unless the same data is to be deposited in successive locations, the SR configuration has to be changed each time deposit is raised. What happens if we address a non-existent location when depositing information? Attempting to deposit in a non-existent location causes a timeout error. Although no visible error message results from this, an error indication can be displayed if the examine switch is subsequently pressed. Pressing examine causes the contents of the SR to be shown in the data indicators. Thus, the operator is informed of his unsuccessful attempt to access a location not included in the PDP-11 address space. The examine switch is used to look at or read the contents of a storage location. The address of this location is predetermined by a load address operation. When examine is pressed, the address is shown in the address indicators and the contents of that address is displayed in the data indicators. Examine is similar to deposit in one respect. The contents of successive locations are shown when examine is pressed repeatedly. The procedure for examining successive addresses is similar to the one we use to deposit data in successive addresses. The initial address is established by the load address operation, and then the examine switch is pressed. The contents of the selected location are now displayed in the data indicators. At the same time, the affected address is shown in the address indicators. If the examine switch is pressed a second time, the address is incremented and the contents of the next location are displayed. This sequence is continued as long as examine is successively pressed. We can ignore the SR configuration when pressing examine. Its contents does not affect the operation. If on examining a location we decide to change the data, we simply place the new data in the SR and raise the deposit switch. We can then verify this data by pressing examine. Load address also affects the examine sequence in a similar manner. If examine is followed by either deposit or load address, the address is not incremented. We never make mistakes, do we? Except once in a while. What do you think would happen if we tried to examine a non-existent location? Data certainly can't exist in a non-existent place. Well, we're immediately informed of our addressing mistake. The contents of the switch register are displayed in the data indicators rather than the data we expected. This is similar to what happens when we attempt to deposit data in a non-existent location. However, in that case, we must press examine in order to display the switch register address. One quick review of the examine switch. When examine is pressed, the address is displayed in the address indicators and the data at that address is displayed in the data indicators. Successively depressing examine causes the data at consecutive addresses to be displayed. The next three control switches are going to be discussed together since their functions are closely related. They are continue, enable halt, and start. The continue, enable halt, and start switches are positioned adjacent to each other in the center of the control switch area. Continue and start are momentary switches that are pressed to activate. Enable halt is a two-position switch. Enable halt occupies a central position in the control switch group, both logically and physically, because it determines if the processor is to be controlled by the program or by the operator. In the halt position, control is exercised through the console switches. In the enable position, the program controls the computer operation. All switches, with the exception of the enable halt and the switch register, are disabled at this time. Let's see how the three switches are used together. With enable halt in the halt position, the consequences of pressing start and continue are quite different. Pressing start causes only a system clear. The system does not start. On the other hand, pressing continue causes the program to perform one step and then stop. Thus, by repeatedly pressing continue, the operator can single step through a program. This is a big help to us if we're debugging either a hardware or software problem. The start and continue functions change if we place enable halt in the enable position. Pressing start not only clears the system, but restarts the program. Normally, this would be at an address established by the last load address operation. Pressing continue in the enable position also causes resumption of program operation. However, the program picks up where it left off, not at the beginning. Remember when we talked about the load address function? We noted that the address in the SR was sent to a temporary location in the processor when load address was pressed. If start is pressed later, after the program is halted, the address in this temporary location becomes the point where the program is restarted. However, if either examine or deposit are pressed subsequent to load address, the address in our temporary location is changed. Now, if the program is halted and then restarted, the starting point is the last instruction we examined or deposited, not the address from the load address operation. The enable halt switch controls how the computer is operated. In the halt position, the console switches determine what actions are to take place. In the enable position, the program is boss. Notice the effect the enable halt switch has on the start and continue switches. The start switch clears the system when enable halt is in the halt position. In the enable position, it also restarts the program. The continue switch is used to single step through a program when enable halt is in the halt position. In the enable position, continue causes the program to be resumed at the point it halted. We'll pause now for a few seconds to allow you to study this flow diagram of these switches. The final group of controls on our console are the system monitor lights. Do you remember the purpose of the monitor lights? Something about maintenance, wasn't it? The monitor lights are used primarily during hardware maintenance or software troubleshooting. At these times, the program can be single-stepped, and the monitor lights indicate the system condition at each point in the program. During normal operation, the operational speed is such that the lights are usually not readable. Most systems have a unique set of monitor lights tailored to the individual system. Of the many monitor lights that are used on the different consoles, only the run light is present on all of them. When this run light is on, the processor is progressing through an instruction. When the light is off, the processor may be in control of the bus and waiting for a data transfer response, or it may have relinquished bus control to another device. On most of the PDP-11 consoles, the run light remains on during a console halt or a programmed halt or wait. Usually, the run light appears as a faint glow. This is caused by the light being turned on and off at a fast rate, the result of normal machine operation. A programmed reset instruction turns off the run light. This concludes our discussion of the basic PDP-11 programmer's console. We've used the 1140 console throughout this discussion since it is fairly representative of the various PDP-11 consoles. For specific information on the other system consoles, refer to your PDP-11 processor handbook. Up to this point, we've talked about the basic console switches and indicators. Now, we're going to learn how to use the console to perform certain functions such as loading, examining, and correcting data, and starting programs. Since you're not yet familiar with the software that's applicable to the PDP-11, we'll use a simple though very important program as the vehicle to learn console operation. It's called the Bootstrap Loader. The Bootstrap Loader is used to load other programs into memory. It can be loaded manually into main memory, or it can be permanently stored in a ROM. We're going to see how the Bootstrap is loaded manually using the console switches. But first, let's talk a little more about how the Bootstrap works. The Bootstrap Loader is used when the memory is empty, when there are no programs stored in it. We all know that a computer can't run without instructions, so in bringing in other more lengthy and more sophisticated programs, the Bootstrap performs an important task. These other programs, also called loaders, are contained on paper tape that is punched in a special Bootstrap format. The Bootstrap Loader can thus be seen as a starting program. It enables the CPU to bring itself up to an operational condition, to pull itself up by its own bootstrap. The Bootstrap Loader occupies 14 word locations in memory. The code for the first instruction is 016701, and it is stored at memory address XX7744. The XX portion of the address is determined by the size of the total memory contained in the PDP-11. XX represents the highest available 8K memory bank. Thus, if the PDP-11 contains 3 8K memory banks, XX will equal 13. In this case, our first Bootstrap Loader instruction is stored in memory location 137744. The last entry in the Bootstrap Loader contains the address of the paper tape reader that will be used as the input device when loading the Bootstrap formatted tapes. In our 24K memory, the input device address is stored at location 137776. Now, let's get back to inserting the Bootstrap instructions into the CPU. The first thing we want to do when loading the Bootstrap Loader is place the power switch in the power position. Remember, for all the console switches to be operable, the power switch has to be in the power position. Next, place the enable halt switch in the halt position and press start. Do you recall what this does? That's right. Pressing start when in the halt position causes a system clear. With the system initialized, we can now proceed with loading the Bootstrap. Still using our example of a 24K memory, place the address of the first instruction, 137744, in the switch register. Then press the load address switch. The address now appears in the address indicators. Now change the SR switch configuration to reflect the code for the first instruction, 016701. When deposit is lifted, this first instruction is loaded into the first assigned location, 137744. It also shows up in the data indicators. To load the second instruction, change the SR switches to read 000026 and lift deposit. The second instruction is now loaded into the next sequential address. Place the instruction in the SR and lift deposit once for each instruction. The address is automatically incremented every time the deposit function is activated. We'll assume that the high-speed paper tape reader is to be used as our input device. This device has an address of 177550, which is placed in the SR switches. To err is human, someone once said, and this is a very easy place to make mistakes. So we're going to verify the Bootstrap loader, just to satisfy ourselves that it was loaded correctly. Verifying the Bootstrap program is a simple procedure. Place the starting address, 137744 in our example, in the SR and press Load Address. Now, press Examine and the first instruction will show up in the data indicators. It should be 016701. Press Examine again, and the second instruction, 000026, is displayed in the data indicators. Pressing Examine the third time should display the third instruction, 012702. But let's say we originally loaded it incorrectly and that the data indicator shows 012712. We'd better correct that mistake or the Bootstrap isn't going to do much bootstrapping. Correcting mistakes is very easy. Place the correct data in the SR switches and lift deposit. Now, verify the results of this action by pressing Examine. The correct instruction should appear in the data indicators. When we press Examine again, the fourth instruction is displayed. Let's see how the Bootstrap loader performs its role in life. As we just saw, the Bootstrap loader is keyed or toggled into the upper 4K of memory from the console SR switches. When the time comes for the CPU to load in a program from the paper tape reader, the CPU retrieves the Bootstrap loader from memory. The CPU, now under Bootstrap control, directs the paper tape reader to send the Bootstrap formatted program to some other part of the upper 4K of memory. That's a brief description of how the Bootstrap loader functions. Now, let's discuss what console operator actions are required to load in a program under the control of the Bootstrap. First, place the program to be loaded in the input device. Make certain that the input device is online and that it's connected to the CPU. The Enable Halt switch should still be in the halt position. Leave it there. Next, place the Bootstrap starting address in the SR switches and press Load Address. The address will appear in the address indicators. We're now ready to start the program. Lift the Enable Halt switch to the Enable position, then press Start. The Bootstrap loader is now running and the program on the paper tape is read into memory. Let's review what takes place. The CPU executes the Bootstrap loader stored in memory. This begins when the Bootstrap starting address, 137744, is placed in the switch register and Load Address and Start are pressed. The Bootstrap loader now directs the CPU to read in the program from the input device and store the program in memory. This continues until the entire program is stored, at which time the operation stops. We'll now consider how to stop and then restart a program. There are numerous reasons why a program might be halted. As one example, a programmer may want to change the contents of a particular memory location to improve program performance. Although we wouldn't normally stop and restart the Bootstrap loader, we'll continue to use it as our example program. The Enable Halt switch is in the Enable position while the Bootstrap loader is running. To stop the program, simply press the switch to the Halt position. This stops the program after the completion of the current instruction. Restarting the Bootstrap is equally easy. First, place the Enable Halt switch back to the Enable position. We can restart the program either at the starting instruction or at the instruction following the one last completed. To restart at the beginning of the program, press Start. To restart where we left off, press Continue. The Bootstrap loader will now run normally, just as if we had never stopped it. This finishes our talk on the console and its use. We'll now quickly review a few of the highlights. The console, we learned, performs 5 basic functions or tasks. They are the application of power, the loading of information into the system, displaying the information, and controlling and monitoring system operation. For each of the tasks, there's a group of switches or indicators on the console. The layout of these switches and indicators varies somewhat for each PDP-11 console. We'll now review a couple of the switches common to most consoles. Additional information on the PDP-11 consoles can be found in the workbook for this unit and in the PDP-11 processor handbooks. One of the switches we talked about is load address. As the prerequisite for the deposit, examine, and start functions, it plays an important role in console operation. Deposit and examine are used to place information in memory or a GPR and then read it back for display on the console. The start switch function depends on the position of another switch, enable halt. The enable halt switch determines how the CPU is controlled. In the halt position, the operator, using the console switches, exercises control. In the enable position, control is passed to the stored program. The switches, with the exception of the switch register, are inoperative. The effect of the start and continue switches, as we also learned, depends on which position the enable halt switch is in. Finally, we talked about the bootstrap loader and the basic program loading function it performs. We also used the bootstrap loader as an example of how the operator goes about manually entering information into the computer. This concludes the study unit on the console. Now it's time to take another self-scoring test. Based on the test results, either review the material in this study unit or proceed to the next study unit. When you hear the tone, turn off this playback unit and take the test located in your workbook.